So in the last class, we discussed the Atterberg limit, which are related to clay soils. These limits are discovered by a scientist named as an Atterberg, and therefore these limits are named after his name, which is nothing but the Atterberg limits. In these limits, we have seen the water content versus volume of a soil graph. That means how the total volume of a soil will vary with respect to the water content. So we have plotted water content on x-axis and total volume on y-axis. Remember, this is the total volume, which comprises of volume of air, water and soil solids. So we have seen there are 4 phases in which a soil can occur. So first phase is the liquid phase, where the soil didn't have an resistance to the shearing stresses. Therefore first phase is the liquid phase. Then we have plastic, then we have semi-solid, and we have solid. So all these phases, we have again got the boundary limits, which is nothing but the liquid limit, plastic limit and shrinkage limit. So we have plotted all these limits on this particular graph. So this limit, which is the boundary between liquid phase and plastic phase, is nothing but your liquid limit, WL, and the boundary between plastic to semi-solid is your plastic limit, and boundary between semi-solid to solid is your shrinkage limit, WS. And correspondingly also we have seen that up to shrinkage limit, still the degree of saturation is 100%. So beyond this shrinkage limit, the degree of saturation is still 100%, but if the water content is less than shrinkage limit, then degree of saturation is less than 100%. That's what we have seen. And always the degree of saturation is in the limit between 0 to 100. So degree of saturation never exceeds this 100% bar. But water content, it can go beyond 1, similar to the void ratio of a soil. So that's what we have seen. In addition to it, I would like to highlight one more point over here. Here this is the volume of the dry soil, that is VD. That means after shrinkage limit, if you go on removing water, it will become a dry. So that means at water content equal to 0%, it will be completely dry. And this is the volume of a soil, which means if I draw the phase diagram corresponding to point number 1, it looks like we have just got the solids and air. There is no water. So the total volume corresponding to this stage is nothing but dry volume, that is VD, and the solid volume is nothing but VS. This is VS, and weight of the solid is nothing but WD as per our standard notations. And if I just go on extending this particular line onto backward side, we'll get an ordinate, small ordinate. That means at x is equal to 0, or that means at a 0 water content, this line, when it is extended back, we got an abscissa, or we got a vertical ordinate. So that vertical ordinate indicates the volume of soil solid, that is VS, which is very, very important, and probably that's what we have left it out from our previous discussions. So remember, if you extend this line, then we will got this particular ordinate when water content is 0, then that ordinate is called as the volume of soil solid. But remember, at water content which is even greater than a liquid limit, and if you go on continuously removing this water out from the soil, the two things will not change. First of all, the volume of soil solid will not change, and as well as the weight of the solid will not going to change. So rest of the parameter, that is total volume means just the you have got here, suppose volume V1, the volume V1 and volume V2. So there is consistently decrease in only the voids, solid voids, and solid volume and weight of the solid will remain as it is. Remember, since we have assumed here that solids are incompressible, particularly soil solids are. And remember, even if you apply any kind of load to soil, there will be reduction in the volume of the voids only. So volume of soil solid will not going to change. This is what is the important assumption in the soil mechanics. So pertaining to all this, we'll see the definition in detail. So first definition is of plasticity index. Plasticity index is denoted by capital I suffix small p. Plasticity index gives the idea about the range at which the soil is plastic. So the range at which soil is plastic is nothing but the difference in water content between at the liquid stage and at the plastic stage. So therefore the plasticity index is nothing but liquid limit minus plastic limit. So here you can see, if you have water content slightly more than liquid limit, the soil will go into liquid phase. So therefore WL minus WP. So this much bound, in this bound the soil will behave like a plastic. So in the plastic stage, the soil has got resistance to the shearing stresses. And remember, in all soils, the shear strength of soil at liquid limit is 2.7 kPa. So it is a standard. So write it over here. For all soils, shear strength at liquid limit is equal to 2.7 kPa. kPa means kilopascal, kilonewton per meter square. So kPa means kilonewton per meter square. I hope you know by this kPa word. So K is over here is small, not capital, but here it is capital. For all soils, the shear strength at liquid limit is 2.7 kPa. May be asked in the multiple choice question. So we have got this plasticity index, and also depending on this plasticity index, we have got the classification of the soil. So if you have plasticity index and the description of soil, if you got the plasticity index equal to 0, that means the soil is non-plastic. And if you got the plasticity index equals to 7 or even less than 7, it is termed as low plastic. And if it is in between 7 to 17, it is medium plastic, and if it is more than 17 it is high plastic. Remember this, which is again maybe asked for the multiple choice questions. So this is the first definition of plasticity index. Further we will go for more definition of the consistency index. And liquidity index. So over here in the alphabet C come first, that's why I'll introduce C first and then liquidity in the later phase. So consistency C and liquidity index L. So these both the limit depends on the water content at the natural stage. So this limit depends on the water content and the natural condition. So that means at present or at natural state, what is the water content? The water content natural may lie here, may lie here, may lie here, or may be here. So it varies based on the natural content. So I denote the natural water content by symbol small w suffix small n. So it is nothing but natural water content of soil. Natural water content, or I'll call it as at present or in situ water content. So remember, I've given a consistency first, that's what, and liquidity second. So this consistency index is denoted by a symbol capital I suffix small c, and liquidity index by capital I suffix small l. So addition of all these two, consistency index and as well as liquidity index, adds up equals to 1. So to remember in smart way, I'll tell you the technique. You have just now seen a definition of plasticity index, which is nothing but liquid limit minus plastic limit. So IP, which is nothing but liquid limit minus plastic limit. So for consistency index, I'll pick up this first term, liquid limit, and I'll place it over here, liquid limit, and I will divide this equation by IP. Similarly, for the second, for liquidity index, I'll pick this term minus WP. I will write it over here for liquid limit, and I will again divide it by the term IP. So since it's a plus, I'll brought this definition of natural water content or at present or in situ water content of a soil. I will just write WC over here. So in order to make this addition equals to 1, I'll have to subtract this WN from this equation. So that's how the definition of consistency index and the definition of liquidity index looks like this. So it is very easy to remember. So in competitive examination, you have to remember so much of formulas. So you must know a trick to remember this formula by a smart way, so that even if you are not thorough with this concept, you can able to solve the problems. But in competitive examination, they may give you this plasticity index, or they may give you liquid limit, plastic limit, and natural water content, and they may ask you to calculate the consistency index or the liquidity index. So remember, so that's how you can remember it. It is a smart way. So depending on this consistency index and liquidity index, it has got practical significance, and it is shown by a smart table. It is like this. So if you have, we have generally 4 phases. Liquid, for liquid phase, the water content, natural water content will be here. This is natural water content for liquid phase. Better I will draw a separate diagram for a liquid phase. This is the liquid phase where you got, this is as natural water content, this is plastic limit, this is plastic limit, this is liquid limit, this is shrinkage limit. So this is the natural water content, and corresponding to this we have this much of volume, in situ volume, V in situ. So at when you have a liquid phase, then Wn is greater than liquid limit. So therefore liquidity index, which is nothing but natural water content minus plastic limit divided by plasticity index. That's what we have seen it from this particular definition: natural water content minus plastic limit divided by the plasticity index. So if you have natural water content greater than the liquid limit, absolutely this natural minus plastic, so it becomes negative. Negative means less than 1. So for liquid we have got consistency index as well as liquidity index, so it is less than 1. So in order to make consistency index plus liquidity index, the addition has to be equal to 1 at all cases. So the liquidity index is less than 1, so therefore consistency index has to be, so absolutely if you got the natural water content which is greater than the liquid limit, so it becomes natural water content minus plastic limit divided by the liquid limit minus plastic limit. So natural water content which is exceeding your liquid limit, that means numerator is greater than denominator, so therefore this ratio becomes more than 1. So liquid limit in this case will become more than 1, and in order to make the definition inconsistent, that means the liquidity index plus the consistency index equals to 1, this consistency index has to be less than 0, that means consistency index will go on negative side and liquidity index will go more than 1. So this is the first case when the natural water content is greater than the liquid limit. So in the next case, if you have the natural water content in between the liquid limit and plastic limit, that means it is in plastic stage, so this is the natural water content in the next phase, that means in the plastic phase. For this particular case, for plastic phase, the natural water content is in between liquid limit and plastic limit. So if you have this particular thing, then the consistency index and liquidity index lies in between 0 to 1. So again here we have 4 subdivided cases depending on the liquidity index and consistency index. So the liquidity index closer to 1, that means the water content is closer to the liquid limit, and the liquidity index even less than equal to 0, that means water content is close to the plastic limit. So therefore here depending on this value of liquidity index and also with the consistency index, we have 4 different phases. namely it has maybe the very soft consistency, very soft. So I'll write it over here as consistency, very soft, medium, and stiff. So again here it is like same way. Very soft means the liquidity index lies in between 0.75 to 1. Soft means 0.5 to 0.75, medium means 0.25 to 0.5, and stiff means 0 to 0.25, and vice versa. This will come it over here. So 0 to 0.25, for soft it is 0.25 to 0.5, medium is 0.5 to 0.75, and stiff it is 0.75 to 1. That's all is about the plastic phase. So if I go into the semi-solid phase, the consistency index will be absolutely, from the definition point of view, the for semi-solid phase you have the natural water content even less than the plastic limit. So if you have the natural water content less than the plastic limit, the consistency becomes much stiffer and stiffer as you go beyond this region, and absolutely you have the consistency index even less than or no, greater than 1, and the liquidity index, yeah, it is less than 0 because it becomes dry and it becomes stiff and stiff. So similarly for solid we have consistency index greater than 1 and liquidity less than 0. But remember, at any case, consider the addition of the liquid consistency index and liquidity index has to be 1 at any case. So these are the classification, and it has got practical significance as well, a bit of these two index, liquidity index and consistency index. We have also seen the flow curve while testing the soil for liquid limit. So while determining the liquid limit, what we have taken a soil passing through 425 micron sieve, and then we have added water sufficiently so that it becomes fluid, and then we have placed it in a Casa Grande tool, and we made a groove of 10 gap, and then we have applied a blows, and we just counted a blows required to close that particular gap. So based on different water contents we have measured blows, and with reference to all these water content and number of blows we have plotted a graph, and absolutely the number of blows we have plotted it on x-axis, and probably this is the logarithmic axis, log axis, and the water content on y-axis. So if you have very high water content, then probably you require very less number of blows, and so we have the points like this. We joined it by a best fitted straight line, and this straight line is nothing but your flow curve. That's what we have defined, the definition of this flow curve, and depending on this flow curve we have one more definition attached to it, which is nothing but flow index, denoted by capital I suffix small f. Flow index is nothing but the slope of this curve, that's all, or slope of this best fitted graph, IF. So in order to define this IF, this flow index will be W2 minus W1. If I take this particular point as a 1, becomes 1 over here, so this is, call it as N1, this is W1, this particular point as 2, N2, and this is W2. So W2 minus W1 divided by log of N1 by N2 to the base 10. Log to the base 10 N1 minus N2 or N1 by N2, and then the same. So from this you will get the definition of the flow index. Again attached to the same curve, if I got the two curves, same axis, number of blows and water content. If I got the two curves, one is like this, another one is flatter, that means which has got least slope. This got least slope, this has got highest slope. So as you go, so it becomes like this and it becomes steeper and steeper. So I'll take this case first and this case second. So if I take the same ordinate of water content, so if I change water content by this much of amount, I will get the increase in strength by this much of amount. So number of blows is indirectly related to your strength for first case. If I extend the same into the second curve, and if I just drop it down and calculate number of blows, then hopefully by decrease in the same amount of water content, you got an increase in strength by much more amount than in the previous case number 1. So therefore as you go steeper and steeper, you'll get this ordinate by less amount and less amount. So this difference in increase in the strength is reduced. So therefore for this particular point of time, I conclude that the toughness or the shear strength, which is indirectly related to the number of blows, is indirectly proportional to the slope of the flow curve, or nothing but a flow index. So toughness of a soil is inversely related to the flow index. That means as this curve becomes less steep or flatter and flatter, the toughness of a soil goes on increasing. That's what is interpreted from this particular point of time. So depending on this, on the same basis, introduce one more term which is called as a toughness index. So it becomes a fourth definition. Toughness index is denoted by capital I suffix capital T. So as I said you earlier, the toughness, which is nothing but a measure of shear strength of a soil, or which is indirectly related to the number of blows, is inversely proportional to the flow index. So therefore the toughness index of a soil is the ratio of plasticity index to the flow index. Remember, which is very important. In many competitive examination, only this definition is been asked. So the toughness of a soil generally gives us the idea about the shear strength of the soil at plastic limit. So if you have the two soils at same plasticity index, if you have the two soils which got the same plasticity index, then probably the toughness index as I already said, which is inversely related to the flow index. Therefore, the soil which has got a flatter curve will have more shear strength. The soil which got flatter flow curve has got higher shear strength. That's what is implicated from this particular definition of the toughness index. So we've seen fourth definition, and then we see the fifth definition of the shrinkage ratio. Generally, the shrinkage ratio is defined as a ratio of a given volume of a soil which is expressed in percentage with the dry volume of a soil. So that means the volume change in the soil expressed as the dry volume of a soil. That means I'll draw a same curve here again, which is volume of a soil and water content. So if I got this particular point number 1 and I got this particular point number 2. So from point number 1 and point number 2 I got the volume V1 and V2. Similarly, water content W1 and W2. So this shrinkage ratio is nothing but SR, which is the slope of this curve, which is V1 minus V2 divided by W1 minus W2. Remember, W is here is the water content. This is the volume change. It is expressed in terms of its dry volume, that is Vd. Absolutely answer into 100 because it's the ratio. Similarly, if I take point number 2 equal to the volume corresponding at the dry and the shrinkage limit, that is Ws. So if I just replace the 2 by shrinkage limit or the condition of water content and volume at the shrinkage limit, probably I got the shrinkage ratio as W1 minus Vd divided by W1 minus Ws, which is shrinkage limit, this whole thing divided by Vd into 100%. If I again rewrite all this expression and I'll replace this change in the water content. So from a basic definition of water content, I'll use another page. From a basic definition, what is water content? Water content is denoted by small w, suffix small w, which is nothing but the weight of the water divided by weight of dry solid, right? Weight of the water divided by weight of the dry solid. So the same way here, the change in the water content is nothing but the weight of water, that is capital W1 minus capital W at the time of shrinkage limit divided by WD. That means weight of the soil at dry condition. That means it is generally the Ws, that means the weight of only soil solid. So this is the same. WD and Ws are one and the same. So that's how this definition goes here. But again I'll replace the weight of water by volume of water into gamma W. If I just do it, so it becomes V1 same way into gamma W minus At the shrinkage limit, its Vd, volume is nothing but Vd into gamma W divided by capital WD. So therefore this expression becomes V1 minus Vd into gamma W divided by WD. So if I just replace W1 minus Ws in this equation and I'll put this particular expression over here, I'll get the shrinkage ratio equals to SR equals to V1 minus Vd whole thing divided by Vd. So here V1 minus Vd divided by Vd, Vd goes over here and this becomes again V1 minus Vd into gamma W divided by capital WD, that is weight of the dry soil solids, or I think dry soil is sufficient because it has the same meaning. Absolutely into 100% because it's a ratio. So this becomes cancelled and we left it out with the WD divided by VD into gamma W. Sorry, over here it is gamma W. So therefore at this place rather than gamma D, it's gamma W. So if you look at over here, WD by VD, what is it? WD by VD is nothing but gamma D at shrinkage limit. At shrinkage limit. So therefore it becomes, shrinkage ratio becomes equals to gamma D at shrinkage limit, because at shrinkage, after shrinkage limit there will be no reduction in the volume. Therefore this is very important at shrinkage limit, because different soil will have different gamma D at different volume divided by gamma W into 100%. So that's how the definition of shrinkage ratio is. So we have just now seen the definitions and the various properties like consistency index, liquidity index, plasticity index, and we have seen what is a flow curve, what is a flow index, what is toughness index, and how it is related, how the stiffness of slope is related to the shear strength of the soil. It gives just the fair idea, not in terms of the quantitative manners. Just if you have the flatter curve, then you can say that the soil has got a higher shear strength. So this is just the relative parameter in order to distinguish from the soil, and you can select a best source for a soil where the soil can be used as a construction material. So after continuation, we in our previous class we have discussed the two major index properties of soil, nothing but soil grain properties and soil aggregate properties. Remember, so this property is independent of the formation of the soil. So this depends on individual grain size. What is its shape, what is its size, what is its specific gravity, and what is its mineralogical composition and all. So these are the soil grain properties, which is a sub property to an index property of a soil. And soil aggregate properties, we have seen it like unconfined compressive strength of a soil, permeability of the soil. We have seen the density index or relative density. The density index or relative density is indicated or denoted by capital S suffix small d, and which is related to only sandy soils, and this term is only applicable to sandy soil. That also we have seen and how to calculate it, and Subsequently we have seen its derivation as well, and also we have seen the property of a clay, which is nothing but activity number, and we probably left it out as it is. So this is still yet to be discussed, but we have discussed all these properties in the depth. So I'll discuss this index property in the subsequent hours. So this activity number, so before going to an activity number, this number has been discovered by Skempton. Skempton 1953 has observed that the plasticity index is directly proportional to the percent finer or clay percentage, or percent finer than 2 micron competence, or we have clay percentage. So he discovered that plasticity index is directly proportional to the percentage of a clay in a particular soil, and absolutely if you go on increasing this, then the plasticity index also go on increasing, because the soil is a mixture of coarse grained soil, sands, gravels, boulders, cobbles, and you have again silts and clays in between. So depending on the proportion of a clay or the percentage of a clay, this plasticity index is related. So it is directly proportional. So if I just remove this proportionality sign and I will introduce by a small constant k into write complete term percentage finer than 2 micron, that means it's a clay percentage generally, and this percent and this constant which is replaced is nothing but your activity number. Therefore activity number is nothing but plasticity index divided by percentage finer than 2 micron. And depending on the same activity number, soil is classified as into following groups. So first, this activity number, if it is less than 0.75, we call it as inactive. So this is a description of soil, and this is activity number. And if this activity number lies in between 0.75 to 1.25, it is normal, and if it is more than 1.25, we call it as active soil. So this part was left it out from a previous bit of the index properties, because at that particular time this definition of plasticity index you are not aware of, this definition of plasticity index. So in order to again define plasticity index, I have to go to the Atterberg limit. That's why I left it out as it is, and we have seen what is this, nothing but the activity number, and accordingly also we have seen this classification depending on the activity number of soil. So we are about to completion of this chapter, which is nothing but the index properties of soil, but few of the things which is left it out from a field point of view, that means field test. We have seen the lab test to evaluate the water content of a soil by pygnometer method or by oven drying method, and there are a number of method which is available which will evaporate water in the soil and will left it out with only the dry soil. So the amount of the water which has gone out divided by the dry solid weight, we get it the water content. So depending on the method and depending on the time availability, we have n number of method to determine the water content. But in the field, this bit was left, that means how to determine the bulk unit weight of a soil in the field. So we can determine it by three ways or three methods. First is core cutter method. B is the sand replacement method. And C is the water displacement method. So we'll see these three methods are relatively easy and probably didn't require much long explanation. See, the in situ unit weight, that means gamma bulk, is nothing but just the weight of the soil, that means a total weight divided by the volume of a soil. So all these methods are divided based on this, how to evaluate this volume of a soil, because even if you dig a hole and the whole by after digging a hole, you can get to know the weight of the soil just by weighing it, but volume of a soil that you have excavated you cannot get to know. So in order to determine this volume of soil, there are three different classical methods. So first is the core cutter method, where we have the core. The volume of core is about 900 to 1000 cc. It varies actually. So the volume of core we know, and we just place dolly at the top of it and we'll drive it by a hammer. We'll give a dynamic load and we'll push this core inside the soil. So once you push this core inside the soil, I assume this as your foundation level, I'll collect the soil inside this core, and after applying dynamic load, once you push the core inside the soil, you loosen the soil surrounding this core. You'll loosen this soil and you'll remove this soil in order to remove and extract the core. So you'll extract the core and you will take the weight of soil inside core. So just do weight by volume, you will get the bulk unit weight by core cutter method. But remember, this core cutter method is not applicable to gravelly type of soils. Remember, this core cutter method is not applicable to gravelly type of soil, because in case of gravelly soil, where the strength of the soil or the gravel size is much more than this diameter of this core, then you cannot probably get the whole thing inside the core. Instead, rather than this core will break. So that's why for gravelly type of soil this method is also not applicable, and also this core cutter method is not applicable for sandy soil, because sandy soil, even if you drive, so once you extract the core, you will not get the total weight inside the core. So if you extract the core, just the soil will lose it by its own weight, so you will not get it. So therefore it is not applicable for gravelly and sandy type of soil. For such type of a soil where it is not able to use this particular method, we have the another method, classical, which is nothing but the sand replacement method. What you will do here, in the sand replacement method, you dig a hole. So original ground looks like this. So we'll dig a hole. So after digging hole, you will take the soil inside the pan and you will measure its weight. So in order to determine bulk density, it is nothing but weight by volume of a hole, right? So you will take this soil in the container. So this container, the container looks like this from plan. We have got a circular hole like this and we take the soil inside it, and this is the hole location. This is a plan, this is elevation, this pan. Then you will collect the soil in this pan, and after collecting the soil in this pan, you will take its weight just by the weight balance. So after calculating weight, one part is over, but the complicated part is still left. How to find it out? Volume of this hole, which is not easy to determine. So volume of this hole is determined by sand replacement method. That's why the name came, sand replacement. What you will do, probably if you have done this experiment in the field, you know this container. This container looks like this, and it has got a flap at this location, or I'll call it wall at this location. So this container is open at top, and you will place sand inside it. Up to certain level, you will place a sand, dry sand. You will place dry sand, and you will take its weight as W1. Okay, then you will take all this container and you will place it on the hole, and you will open this flap. Once you open this flap, you will see the sand going inside the hole. So the sand will occupy this much of volume, right? And also it will form an additional cone like this. It will form an additional cone like this. And it's generally the property of a sand that if you just drop it by a certain height, it forms a cone, and the angle made by the cone with the horizontal, we call it as angle of repose. Do not confuse it with the angle of internal friction. These two are different terminologies. So this is angle of repose. I'll call it as a theta. So after the soil has gone it into a hole, the stage will come at which the soil movement will stop. So you have to plug in this. That means you have to close this wall, and probably the level has got reduced to this one, and again you need to take a reading W2, and again you need to take its reading W2. So the difference between W2 minus W1 will give you the weight of sand inside the hole, right? Plus we have got this additional volume. This additional volume, mark it by black pen. This is additional cone weight. Additional cone weight. So we have again got the additional cone weight. Now what you are supposed to do after this, again here again on the plane table. So this is level 1-1, level 2-2. So at level 2-2, again we have this same dry sand. So at this level 2-2, it's there, and on the plane table you will open the flap and you allow sand to make a cone like this, which was done earlier. So you allow the dry sand to form a cone, and you will take its weight, right? So probably again you've got this level 3-3. So it will be filled with the cone, and you will take another its weight W3. So again here W3 minus previous weight W2, sorry, it's just the reverse of it, because W3 has to be less than W2. So therefore W2 minus W3, you will get the additional weight of cone, right? So you'll get this weight of cone, and you need to deduct this from this in order to get only the weight of sand inside the hole. So after doing this whole procedure, you will get to know the weight of sand inside hole. So for that, in order to calculate volume of hole, you just need to divide this weight by its unit density of a sand, dry sand. You will get the volume of same. But this density of a sand varies with the compactive effort, right? So therefore, in order to determine again this density of sand, you will need to place this whole assembly inside a calibrating pan where the weight and volume of that calibrating pan is accurately known to you. So you will do again the same procedure. After level 3 you will again go and you will place this whole assembly over a calibrating pan and mark it over level 4 again take its weight, and you will note down the weight which is gone inside the calibrating pan and divided by its volume will get the density of sand. So that's how you will get the density of a sand. Probably hopefully the same sand, it is a dry sand. We are not adding water at any stage. So from this density and weight you will get to know this volume of a hole, and the bulk unit weight of or the in situ weight of soil is nothing but the weight of soil excavated from hole divided by volume of hole will give you the bulk unit weight of the soil. So this is a classical way by which, that is nothing but a sand replacement method, by which you will just the measure volume of a hole. This is hole just. The third way is nothing but water displacement method. It is similar to the sand replacement method. Just here the way or the method in which the volume of a soil is measured is different. So remember, this method is applicable for clay soils which has definitely got a particular size and shape. This is a clay soil. So you will weight, so from this you will get weight of the soil, but the volume of soil is determined by water displacement method. So how to measure its volume? It is measured by wax method, waxing technique. So as soon as we dip this soil inside the soil will absorb water, which has to be prevented. So in order to prevent it, you will wax it. You will probably wax it. So after waxing, you will dip the whole soil along with the wax inside the water, and how much volume the soil is going to replace, you will count it, that volume. So volume of water replaced by sand, replaced by soil, which is nothing but VW, right? So but in this VW we have again got the volume of the wax, which this volume includes volume of the wax. So therefore volume of soil is nothing but this VW divided by the weight of wax applied to its surface divided by its density of the wax. So you'll get this volume and you need to deduct it, and that's how you will determine volume. And from the volume, once the volume you get to know, you'll divide weight by volume in order to get the bulk unit weight of the, or in situ unit weight of the soil. So it's nothing but bulk unit weight, nothing but just the weight of soil divided by volume of soil. So this is again the same way, and it is a field method. These are the three different field method to evaluate the unit weight of the, or in situ unit weight of the soil. We have just now seen the core cutter method, in which you drill a core inside the soil and you'll collect the soil inside the core, and you will just take its weight and volume, and you'll divide weight by volume, and you will get the unit weight of the soil. But there got a limitation to this method, because you cannot apply this method for gravelly or purely sandy soil, because you cannot get the lump of a soil inside a core. So in such cases, a sand replacement method is used, where the volume of a hole or the volume of a soil which is excavated is measured by a sand replacement method. And in this water displacement method, which is also applicable for a particular clay type of a soil, the volume of soil is measured by water displacement method. So based on this way, we have again got the mercury displacement method, by which only instead of water mercury is displaced. So depending on how we will calculate the volume of a soil, we have got n number of method, but these three are broad method which the GATE might be looking at asking the question from this area. So we'll look at the example from sand replacement method, and you will get to know the idea how to evaluate the unit weight of the soil, or I call it as more specifically in situ unit weight. So this completes your second chapter of index properties of a soil, and we'll go into the problems right now.